I'm going to talk to you about the evolution of an Android OTA management application. Um, but first of all, let me introduce briefly my company and myself. I work for Kynetics. Kynetics is a company based in Italy and in the US. Um, we provide consultancy and engineering services, and in particular, we develop custom embedded OSs, both based on Android and on Yocto. Um, we provide a product called Update Factory, which is a solution to remotely update embedded devices, and it's based on Eclipse hawkBit. And we are a member of the Eclipse Foundation, which is something that, yeah, we are proud of, and that is very much interesting for this presentation because we developed the Eclipse Hara project. Um, I'm Diego Rondini. I'm an embedded engineer since I would say 2011, when I did my first embedded Android based on Android 1.5. I didn't have an Android smartphone back then, but I did had an embedded Android device. The screenshot on the right is actually Android 2.1, I think. So it's it's actually a bit cheating, but yeah. Then I started to work on Yocto as well. So what I'm going to talk about again is the OTA management application that we have developed for Android. We're going to have a brief look at the history of this project, an overview of its architecture, its components, and probably the most important piece of interest to this group is how we interfaced with Android AOSP system APIs, in particular, of course, to install over-the-air updates. So how did this start? Um, at the Embedded Linux Conference 2017 in Portland, we got to know the Eclipse hawkBit project. In particular, SW Update was one of the frameworks starting to use it on Linux, and Bosch published the source code and made it an Eclipse project just a year before that. It was a really fresh news in the sense that it really provided a very good open source solution that is a server for managing device for updates, and provides a UI, provides management APIs, provides handles to deploy the server on clusters. So it was a really good news for the open source space. Um, we really did like the project, and we decided that we wanted to build a product based on that. So we are providing a service which is called Update Factory, but of course you need not just a server to handle your updates. You need a client on your device to actually connect to the server and to download updates and to install updates. So software update was already doing that. But software update is one of the possible solutions that you can use in Linux and in Yocto based Linux distributions in general. But there are other options. Whereas in Android AOSP, there is a couple of strong points in the fact that Android is already handling updates. So if you want to install an application, you have the APK file format. So it's very well supported. And the same goes for OS level updates. The the format of the update file is mm, a de facto standard in Android, and that's what smartphones are using as well. So a very good technology. So there's both an update file format and all the frameworks that are needed to install um, that OTA or application. What was missing for us was an interface with hawkBit. So a background service able to communicate with hawkBit DDI to manage the states, and yeah, that we were really missing a library. We There was no code using the DDI API, which are hawkBit APIs, to to integrate devices. And again, there was just very few code to look at or um, to actually manage the updates. So let's now see components that make this the software that we have developed, which is actually made up of different pieces. So as I said, we had the hawkBit servers, sorry, the hawkBit server, which we took care to deploy in a cluster on AWS. But of course, we needed um, a background service communicating to this server. In particular, we decided to split um, this application into two pieces, a library, which is called the DDI client, and a background service, which is an actual APK. And we wanted that APK to provide APIs, which we call the Service Consumer API, that allowed third-party applications um, to configure the service and talk to it. So um, why do we want to split part of the code in a library? Of course, we wanted to reuse as much as possible, and really, aside from the installation part, which is of course OS specific and um, depends on the format of the update file and what you are going to update. Um, the rest of the code, and in particular what manages the hawkBit DDI communication, is really something that can be reused, and not only in Android, but in general on any kind of operating system. So we wrote something that is abstract and also can be used from any um, operating system. Of course, there's one requirement, which is the Java virtual machine, but other than that, it can really be used. Of course, Java is a first-class citizen in Android, so that's why we wrote this in initially in Java, and then we rewrote this in Kotlin. Um, I would say this is not the best choice in terms of embedded devices, which often don't have a JVM, but still, if anybody wants to use this in an embedded device that has the JVM, it can be really be used for example, in a Yocto operating system. This whole work that started in 2017, has been contributed as the Eclipse Hara project, and in particular, it's the Hara DDI client component, which is library. The Eclipse Hara project is thought to fill the gap of the hawkBit project, which is the parent project of Eclipse Hara. In particular, hawkBit is designed to provide the core of remote update management. So the servers, the server, and the APIs, the UI, and all that kind of stuff, but doesn't really provide anything to help devices integrate. It's really up to the framework that is integrating the device with the server. As I mentioned before, there is SW Update in Linux, and there is ROC and other that are listed in the hawkBit web page. So this project is meant to provide reference implementation of an hawkBit DDI client. The Hara DDI client is licensed using the APL license, which means that it's kind of like GPL too. So it's fully open source, but you need to publish your code changes under the same license. So on top of this library, we built the Android update service, which manages the Android specific stuff. So it is a background service that communicates using the hawkBit DDI API. And of course, most of the work on that side is managed by the Hara DDI client library, manages the state machine, and most importantly, it handles the installation of different update types, can install application and can install OS updates. And of course, as I mentioned before, it can be configured from the outside. So for example, let's say that you have a third-party application with a UI, because this is just a background service, no UI is provided. The UI can interact, configure the service, get state changes and notifications of what's happening in the background. And again, this is licensed using the APL2 license. APL2 license. This is all the stuff that the update service manages. It manages disconnections, things that can go wrong, different update types, and that kind of stuff. So how did we manage to install application and OSs, knowing that Android already provided the file format and the APIs to install that, but not regular APIs, system APIs. I'm sure all of you will be familiar with the Android SDK. The Android SDK provides an IDE in Android Studio, provides an emulator, APIs, and debugging tools. But that's, of course, something that is thought for applications that go in the Play Store 99% of the times. But as I mentioned, we need to access system APIs, not regular SDKs APIs. So there are two different types of APIs that we need to access. We will see that later in more details, but there are also different approaches to access those APIs. One option is to actually modify the SDK itself. But sometimes that is not needed because if you are going to access APIs that are public but are restricted, what you need to have is actually that your application, the application accessing the system APIs is signed with the platform key. So it's signed with the most important key of the Android AOSP build system. So you're kind of putting your application at the same permission level of um, applications that are embedded in the Android image. So which APIs are we talking about? Um, the update service application manages three different type of updates. Um, it manages application updates using the PackageManager APIs. It manages operating system single copy updates using the recovery system APIs. And it also manages double copy AB updates using the UpdateEngine. And let's have a look at the APK installation. So we use the package manager, and in particular, we use it to get metadata from the APK. Which version of the APK are we installing? What is its package name, so that we can do sanity checks that we don't need to install something that is already at the latest version, and we, for example, don't need to install something that is signed with the incorrect key. We use those APIs to install or update an APK, of course, but we also use them to handle installation errors. So we are getting feedback from the package manager regarding if the update was successful or if any error occurred. I provided the reference in the link here, so I will provide the slides so you can have a look at the code. Again, remember this is APL v2 license, so contributions need to be under the same license. Let's have a look at the over-the-air updates for OS updates. Of course, everybody knows why we need to update an OS. We need to provide new features, fix bugs, or security issues. I mentioned single copy and double copy. What does that mean? It means that, yeah, a single copy system has just one copy of the partitions needed for the OS. In this case, a recovery system, what is called a recovery system, which is a minimal OS aimed at installing the update, is present. So it's an asymmetric design that is opposed to the double copy approach, which has every partition replicated. So there are, again, double the space. It takes double the space. So it was not very common, let's say 5 years ago, but it really provides fallback options. So it's really a big improvement over single copy that were kind of the standard before Android 8. So how did we integrate with the system APIs for single copy updates? We use the recovery system, which is very basic APIs to verify a signature of an OTA package and start the installation of an OS OTA package. In this case, we didn't really have feedback, so we had to look at the recovery log files to actually know if an update was successful or not. Whereas for the double copy OTA, we use the UpdateEngine APIs, and in this case, it was it provided much more information. So the update happens live while the system is running. So you're talking to the background, so the frameworks, and you're getting feedback because it's the update is being installed in the standby copy, and only when everything is done, so the update is ready, the A/B switch happens. So when you reboot. Again, we mentioned that there are two different type of system APIs. The package manager and the recovery system are public but restricted, whereas the update engine is not public. So initially we used to use a custom Android jar. So use a custom Android SDK that allowed us to access those API, but it really was inconvenient because we had to copy a file inside the Android SDK folder. The other approach that we took later is that we actually mocked the UpdateEngine APIs. We used that mock just at build time, and then the update service application was able to use the UpdateEngine APIs at runtime. So that simplified the build process. I think it was a bit more than 20 minutes. Sorry, Chris, for that. But thanks everybody for following me during this presentation. Of course, I'm open to questions.
Okay, well, thank you very much, Diego. That was wonderful stuff, and something that I'm somewhat familiar with the various components of that. So yeah, that's great stuff. So open it out. Does anybody have any questions? Okay, it's kind of quiet out
Maybe
there.
it was too fast, too many info.
So I will be posting. I'm sure you will send me the slides, Diego, and I'll put them on the website, and people will be able to comment and such like on following that.
Okay, great.
But no, this sounds really great. Just one question I have then is, can you give an example of a live system that is using this? Is it widely deployed? Is it deployed on any systems that you're working on?
Yeah, of course. We've been using this really since 2007. There are videos in the Eclipse Foundation showcasing the Eclipse Hara library, and of course Update Factory in action. So yeah, there are plenty of devices. We have more than 100,000 devices connected to Update Factory, and most of them are running Android. So you know that hawkBit is agnostic in terms of the device that connects to it. But we have been using Update Factory to update big devices, and the Android client is using is installed on all the Android devices, and it's running great.
Excellent. It's nice to see a pretty much out of the box solution that would give you over the air update for many embedded Android projects.
Yeah, and I can add something. The Eclipse Hara project is really interesting, but because again it's layered. I mentioned, of course, that one of the users of the library is our Android client, but there's actually what we call the virtual device, which is a simple application that can run, and we test it on Windows, Mac, and Linux, that is really a very easy and quick way to get started with hawkBit. So hawkBit has a Docker container to kind of try it out, and the same goes for Hara. It's a library in its nature, but the virtual device provides an easy way to provide a virtual device and start playing with this code.
Okay. So thank you very much, Diego. I'm going to bring this presentation to a close.